Welcome to lecture 8 of the chapter Coherence, Consistency and Transactional Memory in Multiprocessor Systems. So in this lecture, we will discuss the different methods to detect data races in a program. So if you would have looked at the previous lecture, you would have realized that a data race is an inherent property of a program regardless of the memory model. So the aim is to find a data race in a program. So the question is, how do we detect data races, right? So what we need an algorithm that tests a piece of code for data races. So this means that it needs to exercise all possible control paths, give it all possible inputs, create as many interleavings as possible. And finally, what we have proven in the last chapter is that if there is a data race in a program, it will definitely show up in an SC execution. If it shows up in an SC execution, then so this basically motivated us or gave us an algorithm or a method of how to create these interleavings. Because if you think about it, if there's a complex memory model and we are creating interleavings as per the memory model, that's going to be a lot of work. But if we assume SC, then creating interleavings and different executions is far easier. But even with that, right, we need to exercise as many paths as possible and conclusively prove that there is no data race. And that is quite hard. I mean, there are two ways, of course, but both the ways are reasonably hard. We'll discuss the easier one. So one is a static approach where we analyze the code using a compiler and try to find out if there is a data race or not. So this is computationally hard. It's not easy to do. So what is computationally hard? Well, that is formally dealt with in a course on computational complexity. But let's just say that within a polynomial number of tries, we are not going to get the answer, right? And in some of these problems are also so hard to solve that it is also possible that if we start solving it, the algorithm may never terminate. So that's the reason what we do is we do a dynamic approach where we instrument the program. Instrumenting basically means we just record which variables we are reading and writing to and try to see if there is a data race, right? And so if you run a program millions of times, if there is a data race, there is a very high likelihood that it will show up. So we'll discuss two algorithms. One is the algorithm based on log sets, and the other is the algorithm based on vector clocks. Right. So first I will discuss the algorithm based on log sets. So let us define these two terms here, LV and LT. So LV is the set of logs held by a given memory location. So this is something that our algorithm has to simulate. And LT is a set of logs held by a thread T. Again, our algorithm will have to simulate this. So log is identified by the log address in the sense that every log has a unique log address, which, as we have seen in the previous lectures, we atomically set and unset. So after each access to a memory location V, we modify the log set. So what we do is we compute an intersection. So LT, of course, is a logs currently held by the thread T. So what we do is we compute LV is equal to, we set LV equal to LV intersection LT, which basically means that initially, if let's say we assume that every location is associated with all possible logs, okay, right? So initially, let's say the set of all possible logs is infinity. So what will happen is, let's say the first thread comes and it accesses this memory location. This will essentially be infinity intersection all the logs held by LT, which will automatically become LT. And subsequently, this set will get more and more and more refined, which basically means that for every log variable, we want to find those log addresses that you have to acquire, those logs that you have to acquire to access this location over here. So let's say that we have found out that maybe logs A, B, and C are what you need to acquire. But then let's say another thread comes by which has only acquired locks B and C. Then when we compute an intersection between these two sets, we realize that, okay, maybe lock A is not required because the second thread didn't have lock A in its acquired lock set. So let's remove this and let's set LB as B and C. So what we do is that we continue simulating this algorithm. So the key thing is that at the end of the program, for every variable, for every shared variable, its log set should not be empty. If its log set is empty, it basically means that some thread has accessed this variable without actually acquiring any lock, or it is the case that there are two accesses to the same variable, but the intersection of the log sets is null. So this effectively means that the variable is not protected by the same set of locks. So what is the standard approach? The standard approach for using the lock set algorithm is to add annotations to the multi-threaded code. So these annotations are the ones that help track the lock set. In the sense, the annotations are added to every read and write of a shared variable. And the moment we have a read and write, we track the lock sets. And furthermore, when we acquire a lock by a thread or we release a lock, the lock sets of the threads are also tracked. So lock sets of threads are initially empty and the lock sets of every variable is initially infinite. Right? So for each variable, its lock set initially has all the locks. So when the thread acquires a lock, we add the lock to its lock set. When it releases, we remove. As the program executes, for every variable v, LB keeps getting updated. At the end, if there is a variable with an empty lock set, maybe it is involved in a data race. So we will see that there could be many instances where actually it is not, but it is possibly involved in a data race, right? So basically, this also means that if the log set is empty, it means that there is no synchronization between accesses to the variable. But as I said, all such instances where the log set is empty are not harmful. There are some harmless ones as well. So we will discuss that. So there are, of course, a notion of false positives. In the sense, we will detect many scenarios that are actually not data races. For example, the basic algorithm will flag a data race for read-only variables, right? So let's look at some of these patterns where you will see that a problem will be flagged. For example, when we are initializing a variable, we will typically initialize variables without using locks, right? So the first access, some thread at the beginning will just initialize. So that may not use locks, but will be flagged by a problem by our system, which is not the case. We'll have some read-only variables which are just written once during initialization and subsequently they're only read. Again, that will be flagged as a problem, but that's still not the case. And a reader-writer pattern will multiple threads read a variable concurrently, right? See, even that will be flagged as an issue, but that's also not the case, right? So basically, once the reader-writer pattern could be that a writer writes to a variable, multiple readers keep reading to it. That's not a problem, okay? So to ensure that these read-only variables, which are constants, the reader-writer pattern and the initialization pattern, all these patterns are effectively captured, we need to do something. So here is what we do. So we have a modified state diagram for each variable. So for every variable, we have this state diagram or this FSL, where the variable starts at the start state. The first access to the variable has to be a write, right? Because the first access, you have to initialize the value of the variable. So that has to be a write. So moment we have a write to the variable moves to the exclusive state, which means it is the exclusive property of one thread. In that state, all the accesses by the same thread, whether it's a read access or a write access. So after the thread has made all the accesses, right, or putting it in other words, if you are in the exclusive state, regardless of the read or write by the same thread, we will still continue to remain here, right? So there is no problem up till this point. Now, if there is a read by a different thread, then this could possibly signal the reader-writer pattern. So from here, we'll go to the shared state. The shared state, the connotation is similar to cache coherence, where if there are reads, 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 and reads, we will continue to be in the shared state. So here again, there is no problem. Okay, because this shared state for us is the reader-writer pattern where you write once and then you keep on reading. The problem arises when there is a write by a different thread, which means that we are starting a regular shared access. So there is a write by a different thread either when the variable is in the exclusive state, which means that other threads also are showing an interest in the variable, or from the shared state. So when this happens, we enter the modified state. And in the modified state, our regular log set algorithm runs. Okay, so in this case, our regular log set based algorithm that runs, because if you think about it, we have covered all the basic cases. So the initialization state is exclusive, so we don't detect any data logs here, right? So go back to the three things that we said. Read-only variables. So read-only variables and also reader-writer patterns, both are being captured by the shared state. But let's say if other threads are writing to the variable, then of course there is an issue. And in this case, we enter the modified state and we remain here for every subsequent access, right? Whether it is a read or write, it doesn't matter. We remain here in the modified state, right, for all subsequent accesses. And then we run the regular log set algorithm, right, on the modified state. So this completed the log set algorithm for us. So what are the key takeaway points? Right, so let me just go back once again. So the key takeaway points are it's a simple algorithm where all that we do is we dynamically track LV, which is the vector of logs held by a variable or vector of logs required to access a variable, and LT, which is the logs held by a thread. Every time there is an access, we just compute this. But as I said, that would give us too many of these false positives. So that's the reason what we do is that the first write we ignore, and then subsequently reads the other threads also we ignore. So that filters out a lot of the false positive cases. And the moment there is a write by another thread, it comes to the modified state. And subsequently we run the log set algorithm. So in this case, this prunes out a large number of false positives. So there is incidentally a huge body of research, or there is a great amount of literature that talks about different kinds of data races, false positives, false negatives, and so on. But I'll not get into that. I'll just tell you that the key idea of introducing the FSM was to prune out some of these false positives, right? Such that we can remain with a finer set, right, of possible data races. The other idea is a direct import or inspiration from the world of distributed systems. So here we can think of a classical multi-threaded execution environment as a distributed system. In a distributed system, there is no notion of global time. Okay, so every thread has a local clock, and there is as such no notion of a global time. So what we have is we have a bunch of local times. And whenever there is an interaction between threads, the local clocks are updated. And as I said, there is a certain rule for the local clocks. So if, let's say that there are n threads and each thread has its local clock, there is a certain rule of interaction and that binds these local clocks. But as such, there is no global time case. So assume there are n threads. Each thread, what it does, it maintains an n element vector. It's called its vector clock. So each local clock in this case is not a scalar, but if there are n threads, then each such local clock is actually an n element vector, which is known as its vector clock. Okay. Let's say thread i's vector clock is vi. let Vij, which is basically the jth element of Vi, let it be the best estimate of J's local clock. Okay, right? So let Vij be the best estimate of J's local clock, right? And so the key important point over here is that the element VII, this is the only element which is accurate because this is I's estimate of its own local clock, which is bound to be the most accurate. But for any other element which is not equal to I, such as Vij, this is essentially I's estimate of J's local clock, which of course may not be that up to date or may not be that accurate. But that said and done, Vi is I's local clock, and that is known as a vector clock. So we will use this logic to detect data risks. So what we can do is that we can define some more terminology and kind of define an algebra on vector clocks. So two vector clocks are said to be equal when all their components are equal. So we say that Vi is equal to Vj if and only if for all k, which means for all elements, Vik is equal to Vjk. Two vector clocks are totally ordered. So the precedence symbol over here indicates a total order. For number one, they are not equal. And there exists a k, sorry, for all k. For all k means for all elements, Vik is less than equal to Vjk. So let me explain this again. Vi is less than Vj or precedes Vj if and only if Vi and Vj are not equal. And for all elements, Vik is less than equal to Vjk. So we can also have this kind of precedes or is the same or less than equal to. So this basically means that either Vi and Vj are equal or the or symbol, Vi precedes Vj. So two vector clocks may not always be comparable. In the sense, it is possible that I'll give you two examples. So let's say that Vi is equal to 345 and Vj is equal to 456. In this case, you can confidently say that Vi precedes Vj. However, if let's say Vi is equal to same 345, Vj is equal to 256. So in this case, one thing is clear that for let's say first element 3 is greater than 2, but for the second element 4 is less than 5. So Vi and Vj in this case are not comparable. It is not the case that Vi is less than Vj or it's not the case that Vj is less than Vi. So in this case, they are not comparable. So as I said, two vector clocks may not always be comparable. But if they are comparable, there are some interesting properties. We will look into this. But this is the broad idea of the relationships between vector clocks. So as I said, what again is a vector clock? Well, we can consider each thread a process. A process is a basic entity in a distributed system. Every process is independent. So we can think of every thread as a process. Even though the terminology is quite different, a process in operating system means something else, a process in a distributed system means something else. But in this case, we are talking about processes in distributed systems. So given our definition of vector clocks, let us also define the notion of a message. A message represents an interaction between two threads, right? So an interaction in a classical distributed system would be that let's say, one thread sends a message to another thread over the network. That would be a classical interaction. However, in a multi-core system, we do not have such kind of interactions, but we have another kind of interactions which are nonetheless interactions. So say if a thread I accesses a variable in memory, then it will basically update its state, at least conceptual. And then thread J accesses the variable and its state. So this is a valid interaction that falls under the theoretical definition of a message, which means that if thread I writes to a variable and thread J reads it, right? So even though it's not a direct message, but thread I wrote a value and thread J read it. So that's an interaction. So we have already looked at this in previous lectures. It is called a happens before relationship. And such happens before relationships can easily be enforced or codified in the memory model, where if we set x equal to 1 and another thread reads t1 equal to x, there is a happens before relationship between them, right? Subject to the constraints imposed by the memory model. So that doesn't matter, but because we are primarily looking at SC over here, so once we have a happens before models, that would technically count as a message. So the moment we have such messages, so let's say that it doesn't matter either indirectly through memory or directly via a message, right? A message is sent from thread I to thread J. So here is what we are going to do, right? So what is the idea? The idea is that thread I is sending a message to thread J, where a message is defined in a generic fashion, in a generic sense, as it was done on the previous slide. So what we do is we increment the local clock of I. For example, we implement VII. So whatever was its value, we just do a plus plus. So this indicates that we are starting a new event. So this is done anytime before sending a message, right? So before sending a message, increment the clock, and after receiving a message, right? So J would also do that for VJJ. So this is basically indicating that anytime there is either a message send or a receive event, we increment our local clocks, right? Which is VII and VJJ respectively. Now let's say that thread I sends a message to thread J. When J receives the message, along with incrementing its local clock, which has already been mentioned over here, it updates its vector clock as follows. So for all k, Vjk is set as follows. It's the maximum of Vik and Vjk. Alright. So the maximum of these two quantities, Vik and Vjk. So basically think of this that Vi is something that is being sent along with the message. Vj is the local clock. Then we compute this max operation over here. And the final result is used to increment Vj, is used to replace Vj. So what is the key idea here? The key idea here is that if, let's say, thread I is sending a message to thread J, it is going to first increment its local clock before sending and then send the timestamp. Okay, so timestamp is the value of its vector clock along with the message. What Vj will do is that the moment it gets the message, it will increment its local clock. And along with that, merge both the vector clocks. Vi, which has come along with the message, and Vj, which is its own clock. Merging would basically mean that element-wise take the maximum. Why would you do that? The reason you would do that is that this would ensure that the receiver is at least as up to date as the sender. Okay. So this should ensure that the receiver is at least, so maybe I should add the term at least over here. The receiver is at least as up to date as the sender, in the sense the receiver's view is not older than the sender's view, because whatever the sender has seen, right, of the system, that is, the receiver at least has seen that much, if not more, right? And along with that, it is also recording an additional receive event. All right. So this is the key idea of merging of vector clocks, where the moment there is a message from I to J, what J will do is it will take Vi, which is I's timestamp, and merge it with its own, which is just compute element-wise maximum and element-wise maximum. That would basically tell J that it has the most up-to-date view of the system when we are considering only I and J. As compared to I, it has taken I's updates and merged with its own. So what about vector clocks and causality? Well, we have been looking at causality in the previous lectures as well. Causality basically means if event I happened and that led to event J and event J led to event K. So we have a causal dependence. So let's say that there is a happens before relationship between events ei and ej. We will use vector clocks to track this interaction. So if we have event ei and event ej, let the time of the event in thread I be time vi, and in thread j it be time vj. So we will have the following relationship, and this relationship is being shown without proof. So it is basically saying that let there be for thread I an event ei, and for thread j let there be an event ej, which is happening respectively at times vi and vj. If let's say vi precedes vj, then we can say that there is a happens before relationship between ei and ej. Similarly, if there is a happens before relationship between ei and ej, then vi is less than vj. So one side is easy to prove, the other side is slightly harder. So if there is a happens before relationship between ei and ej, then it means that there will be several intermediate nodes, and because happens before relationship is a transitive relationship, so there will be several intermediate nodes, and for each one of them, if let's say this is k and k dash and so on, the moment I is sending a message to k, we will have vi precedes vk. So this is by definition, this is basically the way, as you can see that in this case, the moment I is sending a message to j, so this is automatically implying that after we are doing this max merging, vi is precedes vj, right? So this follows from the simple logic of the max. So once we have this, we have vk, then we have vk dash, so on and so forth until vj. And since it's a transitive relationship, we have vi precedes vj. It is also easy to prove in the reverse direction that if vi precedes vj, that will not happen unless there is a chain of happens before dependencies, and the chain of happens before dependencies will ensure the other direction, will ensure this as well. So as we have said, we have proven the upper direction first, but the lower one is also easy to prove. So why does this happen? This happens because the receiver has all the sender's updates, and without a chain of happens before edges, the two vector clocks would remain incomparable. But since they are comparable, a chain of happens before relationships would exist. So there is, of course, there are many proofs of this fact, but one thing that you need to kind of believe me is that if vi precedes vj, there is a happens before relationship, and vice versa as well. So this is a very famous and classical result of distributed systems, and the vector clock is also known as Lamport's vector clock. So let us now look at the vector clock based algorithm to detect data races. So we will use all the concepts that we have studied in the previous slides. So the terminology is like this. Let CT be the vector clock of the current thread. Right? This is quite similar to the lockset algorithm. Let CL be the vector clock of the current lock. So in this case, we assign a vector clock with the current thread and a vector clock with the current lock or the lock in consideration. RV is the read clock of a variable v, and WV is the write clock of variable v. So with every variable, we have two clocks, a read clock and a write clock. And TID is a thread ID. So let us now look at the lock operation. So in the lock operation, here is what we do. So what we do, right here, that the first thing that we do is that we increment the current time of the thread, which is basically CT-TID. So recall that CT is the vector clock of the current thread. So we go to its TIDth element and we increment it, which is quite similar to what we were doing when we were sending a message. So in this case, we are doing something very, very similar. After incrementing the current clock of the thread, here is what we do. We do CT union CL. Okay. So CT union CL is basically nothing but the max operation. Okay. So we perform the max operation with the vector clock of the lock that we are acquiring, and this is set as the value of both CT and as well as the value of both CL. So in the sense that the current thread can have some clock, the lock can have some clock, we compute the max of both, which is nothing but the union operation that I've shown. Right, so think of it as a modified union operation, and then finally the max operation is used to set the values of CT and CL. So consider this as a rendezvous point, which means that at this point the lock and the thread, their information is up to date. So after doing this rendezvous, we set the in-lock field of CT. So in this case, a vector clock is an additional field as well called in-lock, which means that it is within a critical section. So we set this to true. Exiting a lock or releasing a lock or exiting a critical section is quite easy. In this case, we unlock. So we set the value of in-lock to false, which basically means we unlock or we release the lock. So what is the most important point here, or the operative part, is that we actually do a rendezvous between the thread and the lock, which means that we perform a max operation and set them to be the same, which essentially indicates to us that now both the thread and the lock are at the same point, right? They are up to date. Okay, so now let's keep going forward. Let's look at the read operation. So when we are reading something, if we are not reading a variable within the scope of a lock, right? So if not ct.inlock, then what we do is that we increment the vector clock of CT, right? So we set CTTID as CTTID plus 1. This is only in the case when this is not being done within the scope of a critical section. Otherwise, there is no reason we will not enter this if statement. Subsequently, we check the write clock of a variable. The write clock of a variable should precede or be equal to CT. Here is what this means. If no thread has overwritten the value after the transaction started, then the read is successful. Let me explain this in a different manner. So let us say that there was a write to the variable and the program is properly synchronized, which means that there was a happens before relationship to a synchronization operation. And then there was an interaction between synchronization operations. Again, another happens before relationship. And then at this point, we are doing the read. So at this point, so when we acquired the lock this time, we set our thread clock and the lock and the clock of the lock to be both equal to CT. So because of the chain of happens before relationships and the property of the vector clock, if let's say there is no data race between them, then this chain of happens before relationships will hold, which means that the write clock should either precede or be equal to CT. So we will discuss when it will be equal to. So that comes later. But it should definitely precede. For this interaction, this relationship should definitely hold. If this relationship is not holding, then this means from this relationship, I'll show you which one. From this relationship, right? So if let's say WV is not preceding CT, this means that between this write and this read, right, which is essentially to the same variable, there is no chain of happens before edges. And if there is no chain of happens before edges, then it's a data race. So we directly come over here. So we can declare a data race. But if there is a chain of happens before edges, then by the property of vector clocks, we'll have WV precedes CT. There is a case where they will be equal, but I will discuss that later. Right? So let's assume that if it precedes or it's equal to CT, then the access is safe. There is no problem. Right? So the access is safe, we enter the body of the loop, right? So in this case, there is no data race. So in the body of the loop, what we do is that we timestamp the value of the variable with the current time of the thread, which means that any subsequent access to the variable will definitely see the fact that the current thread had accessed the variable. All right. So that's the reason that we compute RV union CT, which is something we always do. In this case, the union represents the max operation, right? And then we set its value to RV, which ensures that forever this fact is being recorded that this particular access was made. So now if we just come back, right, we can put this discussion in the correct perspective. I'm just erasing the ink on the slide. You can clearly see that why we are timestamping the lock, right? So why we are timestamping the lock here with the timestamp of the thread. The reason is that we are basically telling the lock, and essentially we are telling the world that a certain thread acquired the lock at this point of time, and at that point of time this was the value of the vector clock, so that later on, if let's say there is a lock acquire, a lock release, and then a second lock acquire, then the second lock acquire, its vector clock will be strictly greater than the first vector clock. So if this is V1 and then this is V2, we can happily say that V1 will precede V2. The reason being that there is a set of happens before edges, and the set of happens before edges are being recorded by the fact that we are time stamping the lock access, right? So the subsequent lock access, the subsequent successful lock access will have the same max operation, and that will essentially ensure that V1 precedes V2, which means that happens before edge between lock accesses is automatically guaranteed. And if you look at again this relationship over here, you can see the relationship between the precedence of vector clocks and the happens before relationship. So this is why we timestamp the locks, right, the acquire of the lock, such that any subsequent acquire will have a greater timestamp. Because it will have a greater timestamp, we can automatically infer the happens before relationship. Furthermore, what we do is we timestamp every read operation, so that let's say if tomorrow there is a write, we can find if the read and write were causally related or not. Like in this case, if we find that the write and let's say the timestamp of the thread, which is when it acquired the lock, if they are not causally related, which means that if we don't have an interaction like this, where there is a synchronization edge and then we read, then we can say that if there is no causal relationship, there is a data race, and we can quickly declare a data race over here. We can do something quite similar for writes. So the idea is again the same. If the write is not happening in the context of a critical section, then we increment the time of the thread, the local time of the thread by 1. We have already seen this. The new part is this. So this is what looks at the causal relationship between the write clock of the variable and the current time of the thread. So as we have argued that any previous write to the variable has to either be equal to the current time of the thread or precede it. If that's not happening, this means there is no happens before relationship between the earlier write and the lock acquire event of the current critical section. And given that there is no happens before relationship, that's why this is not holding. So if this is not holding, we quickly declare a data race, right? Because it should hold, which means that all preceding writes, right? Just go back to the lecture on data races. All preceding writes have to have a happens before relationship with the lock acquire operation that started this critical section, and that will be captured by this relationship. If this relationship doesn't hold, then it automatically means that there is no happens before relationship, so this means there is a data race. Similarly, right, if I look at the read clock, right, so in the case of writes, we care about earlier reads as well, right? So basically two reads, their ordering doesn't matter, but moment there is a write, we care about the ordering of the write with earlier reads as well as earlier writes. So similarly, the read clock also should have a happens before relationship with the current clock of the thread. if an happens before relationship is not existing, then there is a problem and we declare a data race. But if there is a happens before relationship, then what we do is that we timestamp the variable, both of its clocks, the read clock and the write clock, with the current time. And of course, the current time, so we don't discard any updates that are there. So essentially, we take a union operation, a max operation, to RV union CT and WV union CT. Right? So union in this case is not regular union, but it's the vector clock max operation that we have been describing. So here, if you look at this, so having RV union CT is not technically required, even though it has been written to make it look slightly elegant. Given that RV precedes CT anyway, RV union CT will be equal to CT because every element is less than equal to the corresponding element of CT. So we could have very well written RV is being set to the current time and WV is being set to the current time. That also would be correct. So the important point is that any time we do a write access, the write clock is being set to the current time. And subsequently, if you do a read within the same thread, then WV will be equal to CT. That is the reason here we have the preceding and the equal to as well. All right. So what's the key idea? Well, the key idea, if I were to explain it in yet another different way, is basically that whenever I'm doing a read or write, right? So let's say when I'm doing a write, I look at its preceding read clock and write clock, which could have been set in a different critical section. Both of these clocks have to have a happens before relationship with the current time of the thread. If they don't have a happens before relationship, then this indicates a data race. And if they have one, that will be easily captured with these two expressions. And then what we do is we update the times of the read and write times. And if we are reading, then we need not check the read clock, but we just check the previous write clock. And that needs to have a happens before relationship with the current time. And that is easily captured by this expression over here, which, let me erase the ink, is easily captured by this expression. So what happens is we can set RV as RV union CT. So actually the reason that I have kept the union operation over here and not set RV as CT, well, the reason is that in this case we are not really checking if RV precedes CT or not, because it doesn't have to. There's a reader-writer pattern that allows multiple concurrent readers. And if I'm reading, I can continue to read. There is no problem. And so that's the reason there is no need to check if RV precedes CT in this case. But we rather have this expression. So to keep it consistent, here also this expression has been used. But here, of course, as I have said, we could have directly set RV and WV to CT, and that also would have been correct. So this is a fairly simple algorithm, and the crux of the algorithm follows from this equation over here, where we are linking the precedence of vector clocks to a chain of happens before edges. If that is understood, the rest is quite easy to understand, where you can see that what is being treated as a message over here. Okay, let me maybe explain this slide in a slightly different manner. So what is actually being treated as a message over here, let's say between two threads, is nothing but the synchronization edge. Okay. So what we are doing is that when we are acquiring a lock, we are increasing our current counter, right? So let's say there is a thread like this. It comes and it acquires a lock over here. So after this point, let's say its counter is vector clock is CT and the lock's vector clock is CL. So what is essentially happening over here is that for both the lock and the thread is the rendezvous point. And if the thread is successfully acquiring the lock, you can think of this as a message. It's as if the thread and the lock are sending a message to each other, right? So there is a kind of a conversation between the thread and the lock. They're sending a message to each other. And both are saying that we need to become equally as up to date. So that is why they merge their information, which is a union, right? And then both CT and CL become equal to CT union CL. So they come to the same point, which means that any subsequent acquire of the lock, if let's say the vector clock of that is V2 and vector clock of this one is V1, there is a strict precedence relationship. All right. And this is being used in both the read part and the write part. So we read a variable, we only check the previous write clock, not the previous read clock. And the previous read clock is no doubt updated, but updated in this fashion. And let's say for a write operation, we check both the previous clocks, and there has to be a happens before relationship. Otherwise, we declare a data race. Okay, so basically we have discussed a very important component of data race detection. Now what is left is basically transactional memory. Transactional memory is a new paradigm where it is much easier to actually write parallel programs. So we will discuss transactional memory next.